Okay, I'm going to go ahead and get started. So I am Joel Kira, working at Georgia Tech as assistant professor, and I'm going to be talking about kind of generalizations of things that you heard today, kind of really moving towards more open world and open vocabulary learning. So I'm going to start with what is open world learning, kind of contrast it with closed world learning. You already heard a little bit about this from Tyler and others, and really talk about kind of how to move from what is pretty popular these days, zero-shot learning from like CLIP and other foundation models to kind of category discovery and open world learning. I'll kind of talk a little bit about categorizations or different ways that people have approached this problem, and talk a little bit about other applications such as robotics, and then open research problems. So again, Tyler motivated this amazingly well. So the traditional methods that we use these days really are closed world systems. That is, you have a training set, you have all of the list of known categories that is in the training set, you train it, you have a model, and it can categorize those types of things. You've seen in the past few presentations allusions to something like open set learning, which is how do we just detect whether there's unknown things in the data. And so that's a little bit of step beyond, but it still doesn't really cover the case of, can we actually understand what is the unknowns, what classes or categories are they, discover them by themselves, and eventually tie them to linguistic descriptions or automatic labels. And so kind of, again, to contrast this, incremental learning that you've heard about uses label data. Open set learning just says, okay, can I say whether something is unknown or not? Whereas what we want to do is truly open world learning. We want to discover and learn about new categories automatically, ideally from unlabeled data. And these days with language models, we can also actually tie linguistic descriptions to these discovered categories. And so this is kind of where we sit in the space that we talked about in the intro. We're talking about semantic shifts. That is, there are new categories involved. We're hopefully leveraging unlabeled data to discover completely new categories that are in there. And then we want to tie them to linguistic descriptions, that is a vocabulary. So again, this is a great diagram from this paper. And the thing that I really want to focus on is here. Let me turn the laser pointer on. As you notice here, when you're discovering the unknown or novel categories, you see this thing about labeling that from a human, right? And so what we want to do is we want to move beyond this. We don't want to have a human label new unknown things that have been discovered. We want the system to actually by itself group or cluster things together to say, okay, this is a new category, and then automatically assign a linguistic item. So that's really what we're trying to automate, this middle part here, to not require a human. And so kind of this is the dream. What we're doing is there's a range of literature that's kind of building towards this dream. The first part is zero-shot learning, as you know, and I'll talk about this in the next slide, but using multimodal vision and language models, we can now take arbitrary linguistic labels, that is, some new category like a finch, a particular species of a bird, and then have the system automatically recognize it without having it in the training set. But that's really only using one image in order to understand how it relates to the text or the label. What we want to do is move beyond that to actually take the transductive setting, where again, we have a large unlabeled data set, and we want to actually cluster or group many images of those new categories together. So I'm going to walk from zero shot to what is known as the generalized category discovery problem. So for just as background, you may know this already, but models such as OpenAI's CLIP, what they do is they take these kind of paired data sets, so that you have 400 million examples of images with assigned or associated captions or some sort of textual descriptions. And so what this method does is it takes those paired data and learns two aligned encoding. So it takes the text data learns a transformer-based encoder for that, and then you get a bunch of output embeddings for the text. Similarly, you take the image and you have an encoder, like a vision transformer or a ResNet, that again outputs a set of vectors or embeddings for that image. And what it does is it uses contrastive learning to push together the embeddings, text and image embeddings for the paired data, that is the images and their associated captions, while random unpaired data, taken random image and a random piece of text that you know are not, that is unlikely to be actually associated semantically, you push those apart. So that's the contrastive learning objective that they use. And so at the end, you have two encoders that are aligned. That is, the embedding for a textual description for a particular object category is aligned with the embedding for the image of that same category. And so now you can do zero-shot inference using that model. What you do is you're given a vocabulary of potential unknowns. So here, we're not moving to truly open world. There's some hint about what is going to be in the unknown set of categories. And then we feed or create prompts from those labels. So for example, a picture of, for each of these potential things that are in your vocabulary, those generate a set of text embeddings. And then we have a new image and we want to understand what is it. And again, this may or may not have been kind of in distribution. And so what you do is, again, you extract embeddings for the image and you find the nearest neighbor, for example, with respect to cosine distance to all the textual embeddings. And so this is the zero-shot kind of learning paradigm. We'll talk about in the next presentation about a different kind of more composition attribute-based zero-shot learning, but this is kind of the clip style zero-shot learning. However, this doesn't take into account unlabeled data at scale. That is, it doesn't consider all of the unlabeled data that may have lots of unknown things in it. All it does is takes an image and finds the nearest item in your vocabulary. And so we've actually proposed a category discovery problem, and this was around 2016 to 2019. We also called it kind of cross-task transfer learning. And here the problem is, again, like a transductive version of zero-shot. What you have is some labeled data, and this can be auxiliary data like ImageNet or these days clip-style data sets. Of course, at the time when we proposed this, that didn't exist. And then you have a set of unknown or unlabeled data that will have completely new categories. So we don't know what these categories will be, and they're disjoint from this auxiliary data. And so the problem is, how can we discover what's in the unlabeled data? So you can think of this as a clustering problem, essentially, except that you're trying to understand what to learn from the labeled data that can hopefully help you to cluster this. And so this is the problem setting. So given a labeled data set with known categories, you have an unlabeled data set with unknown categories. You want to cluster the unknown, ideally leveraging the labeled data as much as possible. And the evaluation is, you can use clustering metrics, but you can also do, for example, given that you know the ground truth labels for the unknown, you can do like a Hungarian assignment from between the clusters and the labels and try to understand what's called like a clustering accuracy kind of metric. So this is from a survey paper that you see cited below, and it has a nice kind of decomposition of where this setting stands with respect to all the other settings. So we talked about things like domain adaptation previously and things like that. But here, what we have is the labels or categories for the unlabeled data is not available for the training. And so that's why it goes down no here. We have additional information in the form of this labeled set. Of course, the labeled set has completely disjoint categories. So we have to really understand how to kind of what we can learn that's transferable to new types of categories. And so that's kind of here. And again, here in the novel class discovery, it's fully disjoint. That is, the labeled set and the unlabeled set are completely different categories. I'll talk about a generalized category discovery where you're relaxing this assumption. And so at the time, again, in 2018, 2019, we proposed an interesting method for this. where we essentially transform the problem from classification to similarity or metric learning. That is, on the label data, we learned a neural network that just assigns whether two things are similar, that is of the same category, or not, and that's it. And what's interesting about that binary problem is that it's transferable to unlabeled data. We can take that model that can give us similarity, you put it on the unlabeled data. Now you're getting very noisy predictions about whether two things are similar or not. Again, we're applying it to completely new categories from what we learned it on. So it's going to be noisy. It's going to have lots of inherent kind of caveats on how well it works. But once we have those pairwise estimations, we have kind of a learning objective, kind of a neural network to do clustering, basically constraint-based clustering, where the constraints are these two things are similar or the same. These two things are not the same. You kind of have a joint optimization that optimizes a clustering neural network on those large sets of noisy constraints. So there's been follow-on work more recently by Zisserman's group at CVPR last year that generalized this to what's called the generalized category discovery problem. So here, unlike before, the unlabeled data can contain both knowns and unknowns. So this is natural. That's obviously how it's going to happen in the real world. What we want to do is we want to classify the known categories and cluster the unknown categories. And they had an interesting approach. So again, this is a very different approach from what we proposed back in 2018, before all this fancy Dino and all self-supervised learning actually worked really well. And their approach is fairly simple. So you take a Dino self-supervised backbone. And so that really already gives you kind of a lot of information. Again, kind of you could see it as the auxiliary data set or labeled data set being ImageNet, or it doesn't even have to be labeled these days. You just apply self-supervised learning to it. Then you actually adapt this representation to the labeled and unlabeled data sets for this particular problem. So this is adapting the representations, the underlying representations, to the data itself, both labeled, so you can apply supervised contrastive learning, as you may know in the Dino style, or you can combine it with self-supervised contrastive learning on the unlabeled set. So this is updating the representations. Once you have awesome representations that work, that are fully capturing the information in your new data set that you want to jointly classify and cluster, what you can do is just apply a semi-supervised k-means, where you just do k-means on the knowns based on just taking the mean embeddings. Those are the clusters. Then you use that as initialization and add some unknown clusters and then do a joint k-means. So it's nothing like super fancy. It's basically k-means, except that we have a better initialization that comes from the labeled data. So this works fairly well. And I'll show a range of different data sets that category discovery and generalized category discovery are often run on. So of course, there's always the standard like CFAR, ImageNet. Often you'll see subsets of ImageNet. Why is that? Well, because this is a clustering problem. Clustering is super hard when you have very high dimensional spaces, as well as like 1,000 different categories. So there's still a lot of open research problems into how to scale this to very large amounts of categories. And so here you can see kind of the different characteristics of the data sets. And of course, you split the data sets into known elements and then unknown elements. And you can do this within a data set. We can also do cross data sets if you'd like. And so this shows some example performance from the, again, this is not my work, but from Zisserman's group, the generalized category discovery. And you can see unexpectedly, it does pretty well in CFAR, like limited data sets, but has kind of some trouble on other more difficult data sets. One interesting thing you can look at, and this is something that I argue why these foundation models like CLIP don't actually solve the problem. You can look at more fine-grained data sets. So for example, different types of cars or bird species or plant species, and you can see that the performance really drops off. And one thing you'll notice in this evaluation is that we often evaluate separately on the known categories, often called old, and the unknown categories, that is the new categories. How well did you cluster them? And then we have an average metric over both of those called all. But again, the key point is for fine-grained data sets, like herbarium or herbarium, it actually doesn't do very well. And this is even, we'll show with CLIP and other kinds of representations. Okay. So there's a large number, and you'll see kind of, again, increasing number of publications in the past year or so. It's just really exploded. And they focused on a large or several different categories of methods of improvement. Of course, we want to use better representation. So you already saw, these methods being updated to Dino and self-supervised learning. And we'll see kind of further improvements when we add things like CLIP and other multimodal representations. We can improve the similarity learning part. So as I mentioned, we use like a neural network, like a Siamese type neural network to learn what's similar or dissimilar. And we can, of course, do better. So there are these ranking statistics that other groups have come up with that can much better determine whether two images are of the same category or not. Once you have the initial representation, you can also, again, fine-tune your representation, because now we have awesome contrastive supervised and self-supervised methods. And so there's a range of kind of different training methods, some that are multi-stage, you do like self-supervised first, then you do fine-tune on the label, then you do another kind of contrastive self-supervised on the new target unlabeled data set, and so on. And then, of course, this is deep learning, so we can often change things like the objective or loss functions. And this is really where you can boost performance, because, again, the key problem is like, what can you transfer from the labeled data set that has some set of categories to really that is generalizable to the unlabeled data set that has completely new categories, which, as we know, is a very difficult problem. So people have come up with kind of the typical, bag of tricks that people have been developing over the past years, like better clustering methods, better pseudo labeling methods, where you can actually train something and then estimate on the unlabeled data. Ideally, jointly learn over this labeled and the unlabeled data. Of course, you can apply things like meta learning and so on. And then one interesting thing that I've seen come up in the past really recent papers is understanding the label structure. As you can tell, we're trying to generalize from known categories to unknown categories. And if we understand the relationship between those two sets of categories, for example, their hierarchy or some other like knowledge graph-based representations, we can hopefully even better eke out what we can learn from the labeled portion. So, I just put up a few papers, not to say any of the other papers that are not here are not good. There's lots of really amazing work, so you should check it out. I'll have a link to there's a nice, awesome, category discovery webpage that has all of the recent papers. So I encourage you to check those out. It's a very fast moving field. I think the pace has been increasing like crazy. Okay, one key challenge that I think a lot of works perhaps ignore is understanding how to choose the number of clusters. Again, you have unlabeled data with some set of unknown categories. I don't know how many there will be in there. So usually people start with the obvious, which is just set the number of categories to the true number of categories in the unknown data. Of course, that's kind of leaking information in some sense. And so there's been a range of methods that try to actually estimate, okay, given this unlabeled data, how many new things do we actually have? In the method that we proposed way back in 2018, this actually came from free because we had a neural network do the clustering. And it turns out if you over-represented the output space, like the number of nodes in the output, it actually tended to ignore the kind of excessive nodes and only clustered or assigned images to some subset of those nodes. And so we could estimate to some degree how many unknown categories. Of course, it wasn't perfect, and subsequent works improved upon that significantly. Of course, there's like traditional clustering algorithms that have these like number of cluster estimation, like k-means plus, and so on. And there's other kind of more sophisticated methods. There's some methods that actually use the labeled data to kind of probe, am I discovering or kind of tuning the hyperparameters of these clustering methods? in a way that is discovering the accurate number of categories on the labeled data, which I know, and hopefully that'll generalize to the unlabeled data. There's also recent methods. Actually, there's a paper here that you can check out on Gaussian mixture models for this. And in that they really do emphasize discovering the number of categories. So check that work out. Again, not our work, but great work at ICCV. And again, you can kind of actually quantitatively assess this. So you can have, for example, given the data set and the true number of ground truth categories, is my estimation method actually predicting how many categories there are? And in the beginning, these methods were not so great. And then over time, we can better and better estimate the number of categories. But again, I'd like to emphasize this is not a solved problem by any means, especially as we scale the number of categories. This gets much more difficult. So I do encourage, if you are interested in this field, to really focus and emphasize your methods working under the condition that the number of categories, unknown categories, is not available to you. Okay. So as I mentioned, language can be really useful here. These models that align the image representations and the text representations. We can do zero-shot learning with just an image. Clearly, this can help if we do this transductive clustering setting as well. And so there are several ways to leverage vision and language models. The simplest is take Dino, replace it with CLIP. This is something that we've done. You'll see the citation below, but other groups have as well. And you can see replacing Dino with CLIP actually helps. And this is not surprising. CLIP is awesome. It has great generalization. It has 400 million examples. So the range of categories that they have there is really quite large. And so kind of you can see pretty substantial gains over many different data sets using CLIP. And we've done a lot of analysis on exactly when this happens and things like that. So check out these papers. There is a caveat here. It's a little bit controversial to use CLIP for category discovery because people say, well, is this actually discovery? I don't know what's in CLIP. OpenAI hasn't told us. And so are you actually discovering? And so my response to that is often, again, these models do not solve the problem. In the especially fine-grained data sets, CLIP still doesn't do very well. So it's still kind of, not an easy solution. And again, there's lots of awesome works by other groups that you should check out, also leveraging vision and language models as well. Okay. And so one kind of method that we've also leveraged multimodal models in is a little bit different, which is the notion of retrieval. If you're on Twitter, you know that people love retrieval plus LLMs. So here we're actually using retrieval to solve or improve upon the solution for category discovery. Specifically, what we can do is, okay, in the original setting, we have the unlabeled data and we have the labeled data. We can extract their representations and then do some semi-supervised clustering method. What if we actually retrieve pieces of text that might help us? The idea is maybe these are unknown categories, but maybe there's some random Wikipedia or whatever webpage that has some linguistic descriptions that relate to what this new category attributes or characteristics are. And so what we do is, given the image, we again extract the CLIP encoding, and then we retrieve from some large text corpus. Now, this text corpus does not have to be paired with images. It's just some random, it could be any web crawl. And what we do is we extract the top K pieces of text that have embeddings closest to the image. And then we add the embeddings of that pieces of text to the actual clustering. So you can think of it as a multi-view or co-clustering kind of method. And so this is showing the specific kind of method where we have, again, we have images, we have retrieval of pieces of text. And so the image can be seen as a view of the data, of the semantic thing that is in the image. However, you can view this text as, in some sense, augmentation or a multiple or another view of the data, of the same data, because these text pairs hopefully describe something in the image. How do we know? We know this because we, again, did multimodal retrieval. And then once you have that, you can do a multi-view clustering kind of approach. And so while GCD kind of with the clip instead of deno already increases performance, we have even better performance with our retrieval-based methods on top of that. And this kind of generalizes to more, again, fine-grained categories, which is, again, much more difficult. However, you can see that now we're starting to get, beyond the kind of 30s and really low accuracy values that these fine-grained categories have in discovery. Okay, there's been lots of other works in category discovery, ranging from 3D and 2D segmentation and object detection, federated learning, and so on. So it's really a field that has really taken off. So again, category discovery generalizes zero-shot learning across one axis. That is, rather than just taking an image and doing zero-shot inference on it, we actually take the transductive setting where we had lots of unlabeled data. We can also generalize across the other axis, which is the vocabulary. So if you remember zero-shot learning, we often use we call it zero-shot. That is, we're trying to classify unknown things. But in reality, we actually give it a vocabulary, often pretty small, that actually has the things that will be the quote-unquote unknowns. And so we can think about how do we actually increase the vocabularies here, all the way from tens of thousands of nouns, all the way to hundreds of thousands of concepts in some knowledge graph like ConceptNet. And so kind of these methods like open vocabulary detection have kind of started to do that. These methods are, again, starting from not 10 or 100 vocabulary sizes, but maybe like tens of thousands or 20,000s. As we know in object detection, we actually have these very large data sets. And so one of the kind of early papers in this field is called Wild, which has several key components. Again, it's leveraging CLIP to do this kind of zero-shot object detection. And so what it does is uses kind of first changes the object detection pipeline to make it produce class-agnostic proposals. So moving from image classification, zero-shot, to open vocabulary detection, it's actually complicated. Like these object detection pipelines, as you know, are very complicated. There's like proposal stages and classification stages, and there's multiple parts to the pipeline and dozens of hyperparameters and things like that. So the first change was just changing the objectness score, so to speak, and what is a proposal that might have an object in it into something that's class agnostic. And then using a CLIP embedding, of course, to given a region, what is this class? So it's using the same zero-shot kind of method using CLIP. However, because we have these very specialized detection pipelines trained on COCO and other things, we can basically do a knowledge distillation step where we take the model that's learned from CLIP, that's these like aligned vision and language, and distill it through distillation losses into the object detector part of the model itself. So again, this is like open vocabulary detection has blown up. And so even in the past year, it's just been dozens and dozens of papers doing many, many different things. I don't have time to go into it, but feel free to, there's this really nice survey paper that I cite here that has a lot of different methods, but ultimately it's very similar, pseudo labeling, all these kinds of things as well as really aligning the linguistic descriptions to the actual object proposal. So again, the key difference between classification and detection is that we have this messiness of many object proposals everywhere. And so we want to align those object proposals to the language part as well. So for example, there are methods that, again, do this distillation from the vision and language model. However, they actually do an association between parts of the textual description and particular bounding boxes. So it has this explicit mechanism in the neural network itself to do the grounding or association between those. Okay. One thing that I'd like to point out is we really, again, want to move into open world. To me, open world means everything and not just word descriptions or labels, which are quite arbitrary. And so we want to move towards actual large semantic descriptions like car with a dog in it that's blue and it's a truck, something like that. That's much more complicated. It has relationships between objects and things like that. So recently there's been kind of this methods that have combined two fields, open vocabulary detection and something called referral expression comprehension, which is basically, again, the grounding problem, aligning pieces of text with particular bounding boxes in the image. And so there's this nice paper, again, that I cite here on the bottom that's kind of showing that open vocabulary detectors can't really handle this. They usually just handle single word labels. And so like handling complex descriptions requires a little bit more. So it requires kind of global and local pre-training. So as you know, all these image-based pre-training methods, they may or may not focus on object level information, or certainly not localization. You do get that a little bit for free from Dino and other kind of methods, but not doing as well as doing it explicitly. And so there's kind of these self-supervised or pre-training methods that actually do it at the local region level, not just at the image level. And it also requires this something that's very common in referral expression, which is this reconstruction. So you take the particular components or like bounding boxes and things like that, and then try to reconstruct the textual description. This ensures that you have sufficient local information captured that's enough to reconstruct the actual text or the words themselves. And then there's lots of dealing with things like false positive rejection. One thing that referral expression comprehension doesn't do is it assumes that the description in the text actually appears in the image. But what if the text happens to mention things that are, or objects that are not explicitly in the image? And so you need to deal with like these kinds of methods as well. And then finally, we want to move to some work that's called vocabulary free classification, which looks at how do we, again, move from, tens of items in your vocabulary to tens of thousands of items in your vocabulary, all the way to hundreds of thousands of items in your vocabulary. And maybe we can use these knowledge graphs, such as ConceptNet, that actually encode the relationships between the categories themselves. So again, this is a kind of truly open world where we have all the concepts that humans have put in ConceptNet over dozens of years, and we want to actually discover new things in the world and somehow map them, either particular nodes in this knowledge graph or even combinations of nodes, to get this compositional generalization. And again, I think one thing about open vocabulary and open world methods is that there's lots of cool applications, such as in robotics. So in robotics, we also want to handle novel objects. As an example, if you learn a reinforcement learning policy to manipulate objects, such as grasp them, again, you have the same IID problem. If you apply that reinforcement learning policy trained on one particular distribution of objects, when you apply them to completely novel categories, the degradation is quite severe. And so you can think about maybe combining these discovery methods, actually discovering new objects, understanding their relationships to prior objects that were in the training set, and then reasoning about how to manipulate those objects. So I'm going to give a plug about a kind of NeurIPS challenge that I'm involved with, led by Chris Paxton at Meta, which is, and Meta has been doing a lot of the work on this, looking at really this open vocabulary mobile manipulation. So again, generalizing to not just new objects, but new receptacles. So if you're trying to put different objects from the fridge into drawers or whatever, then you change the receptacles during testing time as well. And this will actually be tested both in simulation, but also in real world robots in similar scenes or slightly out of distribution scenes for the top winners. So I do encourage you to check that out. Okay, so with that, I'm going to conclude with kind of open research questions. Again, this is a really exciting area, but there's still a lot of challenges. One is, of course, just achieving the dream. We want to combine this with continual learning, as was mentioned. We want to just continuously discover new things, somehow learn representations and classifiers and detectors for those new things, figure out how they linguistically align with the prior things that we knew, and so on, just as humans do. As part of that, there's understanding what is novel, actually. I think in the era of foundation models, there's always a question of what does novelty mean and things like that. So I think there's a lot of interesting questions there. When you combine it with vision and language models, now we have SAM, like segment anything, and so on. So again, there's a lot of cool both opportunities and challenges as well to leverage those. And again, we'll talk, I think we'll have another talk at the end about vision and language models. We want to automatically discover new categories, but also assign linguistic items to them. And finally, how can we scale this to really real world, large scale vocabularies that hopefully cover all known concepts, both current, but also new concepts that appear. As an example, my student likes to use kind of the Apple VR headset just came out, right? That's a new category. It looks different, but it's kind of mixture of things that have existed before. So with that, I'm gonna wrap up with some resources. Again, these awesome web pages are awesome. So they have a cool updated list, and you can feel free to check those out. And with that, I know I'm a little bit over time, but feel free to take questions. Thank you.
Does anybody have any?
Thank you for your talk. I like to you elaborate more on how should we define awesome. I think one problem that I have is I feel like right now we use access to help discovering it with objects constantly. But I also think that it's possible to come up with a way that you can use to come up with the object. I mean, the concept as well without language.
Okay, that's a great question. I mean, to be honest, I'm not a fan of categorization in the sense that I think objects categorizations are kind of arbitrary in some sense, right? You can, if you give me like thousands of objects, some people might have one, taxonomy for that. Another person might have different taxonomy. So really, that's why I'm a believer in language, right? So we have arbitrary linguistic descriptions that somehow describe these categories. And those can be, again, what language gives us is compositional generalization. That is, you can arbitrarily compose many different things, related to the things that we do know and that we've seen in the past, but that describe new things, right? So humans, for example, if I describe, like an elephant car, for example, you can envision this, right? Just from that linguistic description, you may not have ever seen an elephant car. And so I really am a believer in moving towards, again, arbitrary descriptions and then being able to get detectors and classifiers for that automatically.
Yeah, thanks for the talk. A lot of information. Here, my question on what we want relates to the teaching as well. I think maybe you started off with the class involved, the learning about the class are different. That actually the key solving this problem in the framework. If you have all the training sets in the world, you finally have that similarity, right? The problem is, of course, that you do that problem. The one thing is that at a certain level, you will tell them that yeah, I would see the role of taxonomy is how do you do that to generalize to certain specialist domain. It's not like the biologist about that. That's a slow verb. That's not
Yeah, that's a great question. I mean, I think, yeah, kind of related to my assertion that I like language. I think knowledge graphs or taxonomies are really useful as well. Depends on the domain, right? So I think in many domains, we can actually have taxonomies. Of course, biologists, I'm sure, argue over these taxonomies. We have very, hard data, such as genetic information, right, to derive those. And so I think given a taxonomy, it's an interesting problem of mapping new data to elements of that taxonomy through, for example, hierarchical clustering or other kinds of methods. I think you're really getting to the heart of the problem and something that I think people will be tackling moving forward, which is understanding the structure of the labels in the unknowns and mapping them to either given taxonomy that can be, specialized for the domain or more general ones like concept nets. So I completely agree. I think modeling such taxonomies and hierarchy, like the hierarchies is really important. And then mapping them, if you in a particular domain have them, mapping them to those, I think is a like really rich way to do similarity. Because like you said, a flat similarity, you know, that just says two things are similar or not is not enough to really do well at this task.
Question is also how open.
I think, again, I think it should support any arbitrary thing that a human can come up with, ideally. Mhm. Okay, I think, so I couldn't quite hear, but I think the question was basically if you have more fine-grained subclasses and discovering those rather than.
Actually, new issues.
Right.
From the world of focus, rather than fine-grained. So we're looking for very subclasses.
Okay. Yeah, I mean, I guess we can take it offline, but I think fine-grained and then just understanding, again, like, I think typically these methods are much, as you saw, the performance is much lower for anything that's much more fine-grained or subclasses or sub-distributions of like a larger sets of categories. So, and you do see like new papers that focus on that setting, where this specifically we focus on data sets that have like those properties that you mentioned. Yeah. So I do think that's a valuable line that is coming up and is really the more challenging case.